Motion and integration. Okay, so you know that if you differentiate velocity, then you, with respect to time, then you get acceleration. So if you were to do the reverse of that, integrate acceleration, then you'll get velocity, which is what this is saying here. Likewise, if you were to differentiate displacement, then you get velocity. So if you were to integrate velocity, you'll get displacement, which is what this is saying here. So we've got two examples in a past HSC question. Alright, the first example then says the velocity of particle is given by this. Initially the particle is 2 centimetres to the left of the origin. So that bit there means when t equals 0, when t equals 0, the displacement, which is x, is 2 centimetres to the left, which is -2. Alright, find its displacement after 5 seconds. So we're given an expression for v. So to find displacement, we need to integrate, okay, because displacement is equal to the integral of velocity with respect to time. Alright, so let's integrate the velocity, which is integrating 3t squared plus 2t plus 1 dt with respect to time. Integrating 3t squared, add 1 to the numerator and divide by the new numerator. Integrating 2t and integrating 1. And you always have a constant of integration. We're going to use this bit of information here to find our constant of integration. When t equals 0, x equals -2. So then you can clearly see 0, 0, 0. This is -2, then you can see c is going to equal -2. So I would even write that down. When t equals 0, x, that's with your comma, equals -2. Therefore, c equals, sometimes if it's not such a straightforward substitution, you can actually show the substitution to work out what c is. So then our displacement x is going to be t cubed plus t squared plus t minus 2. And to answer the question though, find its displacement after 5 seconds means we need to substitute in t equals 5 to find the displacement when t equals 5. So that's going to be 5 cubed, 125, plus 5 squared, which is 25, plus another 5, minus 2, and what do we get? 153. And what units was this in? Okay, velocity is in centimetres per second, so that means displacement is just going to be centimetres. Alright, so to answer the question, find its displacement after 5 seconds. So after 5 seconds, the particle is 153 centimetres to the right of the origin. Okay, and you could even, don't be afraid of using words to actually answer the question. After 5 seconds, the particle is, are we talking about a particle? Yes, it's a particle. Is 5 centimetres, sorry, 153 centimetres. Where did I get 5 from? That's not letting me erase that, so I'm going to have to just put some lines through. 153 centimetres to the right of the origin, because there's positive displacement. Positive 153 means to the right. Alright, part B says find the distance travelled by the particle in the 3rd second of its motion. So in the 1st second is from 0 to 1 second, in the 2nd section is from 1 to 2 seconds, and in the 3rd second of motion is from 2 to 3 seconds. So where is it at 2 seconds, and where is this particle at 3 seconds? And the difference between those displacements is the distance the particle travels. So that's one way of working it out. Another way of working it out is finding the integral between 2 and 3 of the velocity, or x equals the integral between 3 and 2 of the velocity dt. Now this, you can only use this method if the particle does not change direction in this time period. So does the particle change direction between 2 and 3? Well, how can you find when a particle changes direction? A particle changes direction when the velocity is 0. So here's our expression for the velocity. If we made that equal to 0 and solve for t, we can find when the particle is at rest or when the particle changes direction. So just as a little aside, let's make the velocity, which is 3t squared plus 2t plus 1, let's make that equal to 0 and solve for t. Well, we can't factorise that, so let's see if we can use the quadratic formula. T equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now you can see the discriminant there is going to be negative, which means there is no solution. And what were we trying to find the solution of? Well, we're trying to find the solution of when the velocity equals 0. So if there's no solution, that means the velocity is never going to equal 0, so the particle is never at rest. Which is good because never at rest, because that means then that we can use this integral to find the distance travelled in the third second, and the third second is between t equals 2 and t equals 3. Okay, so let's go back and find that integral, which will be the distance travelled by the particle. Let's see if I can just erase this stuff in green to make a bit more room. Yep. Okay, so integral between 2 and 3 of the velocity with respect to time. Whoops. Accidentally pressed a button there. I shouldn't have. So velocity is 3t squared plus 2t plus 1. We are integrating that with respect to t, which we already kind of did over here in red. Except this time, because it's a definite integral, the constant of integration does not matter. So there we go. And substituting 3 in, 3 cubed plus 3 squared plus 3 minus 2 cubed plus 2 squared plus 2. And we get an answer of 25. So the distance travelled by the particle is 25 centimetres. Alright, so that's one way of working it out. Another way is if we were to work out, like I said initially, work out the displacement when t equals 2, work out the displacement when t equals 3. The difference between them will be the distance travelled, so long as the particle does not change direction. And we already worked out before in green that the particle is never at rest, so it's not going to change direction between these two times. So if we were to do that, let me just rub out some other stuff to make some room. What happens when I do that? No, undo that. No, can't really rub anything else off. Let me just see if I can use another colour. When t equals 2, subbing into our equation for our displacement, subbing in t equals 2 here, what do we get for x, the displacement? We get 2 cubed plus 2 squared plus 2 minus 2 is 12 centimetres. What about when t equals 3? What do we get? 3 cubed plus 3 squared plus 3 minus 2, which is 37 centimetres. And you can see the difference between these two values. 37 centimetres minus 12 centimetres is also 25 centimetres. So you can see the distance travelled is 25 centimetres using two methods there. All right, another acceleration of a particle is given by that. Particle is initially at rest. Remember, initially means when t equals 0. At rest means when the velocity equals 0. 1 meter to the right of the origin means the x, the displacement, is positive 1. So this is saying when t equals 0, our velocity equals 0, and x equals positive 1. So that's what that bit there is saying. Find its exact displacement after 9 seconds. So we're given acceleration, and we need to find the displacement. So first we have to go from acceleration to velocity, then we'll go from velocity to displacement. Then we'll sub in t equals 9. So this is our expression for the acceleration. How are we going to get velocity? Well, acceleration is the derivative of velocity with respect to t. So to get velocity from acceleration, we need to integrate. So we need to integrate this thing here. And it's going to be easier to integrate if we use what we know about index laws to change t plus 1 all squared to an easier form. So I'm going to rewrite the acceleration as 6 minus 2, and then we got t plus 1 to the negative 2, and that means that's going to make it a lot easier for us to integrate. So velocity is the integral of acceleration with respect to time. So it will be the integral of 6 minus 2 t plus 1 to the negative 2 with respect to time. So integrating 6, and you just get 6t. Integrating this bit here, we want to add 1 to the power. So negative 2 plus 1 is negative 1. Divide by the new power. Divide by the derivative of whatever's inside the brackets. The derivative of t plus 1 is just 1. And then we have our constant of integration. We can write this a little bit nicer using our index laws again. The negative 2 actually and the negative 1 on the denominator, that negative and that negative is going to make a positive 2. And we can rewrite t plus 1 to the negative 1 as over t plus 1. Okay, we're going to use our important bit of information up here given the question to find our constant of integration. When t equals 0, velocity equals 0. Let's sub that in to find the constant of integration here. So, and I usually write, when I'm finding the constant, I'm writing what information I'm using. So when t equals 0, velocity equals 0. So what 0 equals 0 plus 6 times 0 is 0. 2 on 0 plus 1 is 2 plus c. So then you can see that c equals negative 2. So our expression for our velocity becomes 6t plus 2 on t plus 1 minus 2. Alright, so we've got our expression for our velocity, but we want to find displacement. So we need to integrate again because velocity is the derivative of displacement. So displacement is going to be the integral of velocity. So change colour again. X is going to be the integral of velocity with respect to time. So that is the integral of 6t plus 2 on t plus 1 minus 2 dt. Okay, so the integral of 6t, add 1 to the power, divide by the new power, t squared, so it's going to be 3t squared. And remember, all the time, whenever you're integrating, you do a mental differentiation of this to make sure you get back. Just like when you're expanding and factorising. When you factorise something, you do a mental expansion to check your answer. Always doing that with integrating as well. So differentiating this, you'd get 6t. Yes. Cool. Okay, integrating 2 on t plus 1. If we were to rewrite t plus 1, just like we rewrote t plus 1 and negative 2 here, if we were to write that as t plus 1 to negative 1, like how we had it here, and then we're to add 1 to the power, negative 1 plus 1 is 0. And remember, that's the indicator. You can't do that because you can't then divide by the 0. So that means it's a log, and it is going to be 2 log of the denominator. And then integrating negative 2 becomes negative 2t. And then we have our constant of integration plus c. So we're going to use this bit of information up here to find our constant of integration. When t equals 0, x equals 1. Okay, when t equals 0, x equals 1. So that's just the information that was given to us in the question. So we've got 1 equals, substituting in 0, that becomes 0. This becomes 2 log of 1. Log of 1 is 0. Then we've got 2 times 0 is 0, so our c is just 1. So let's rewrite our displacement. X equals 3t squared plus 2 log of t plus 1 minus 2t plus 1. And we're going to use that to actually answer the question. The question says find its exact displacement after 9 seconds. So that means we need to substitute in t equals 9 to find x, which is our displacement. So that becomes 3 times 9 squared plus 2 times the log of 10 minus 2 times 9 plus 1. And that equals, it says exact displacement, so that's going to be 226 plus 2 log 10. Okay, and that will be, what units will that be? Well, velocity was in meters, acceleration was in meters per centimetre squared, so that means velocity is in meters per second, so that means displacement is just in meters. Alright, the velocity of a particle moving along the x-axis is given by that. X is in meters, t is in seconds. Initially the particle is 5 meters to the right, so that means when t equals 0, x equals 5. Show that the acceleration of the particle is constant. Okay, so we are given x dot, which is the velocity, is 10 minus 2t. How do we get the acceleration from the velocity? Well, acceleration is dv dt. It says show. So you want to show the marker that you know, what you know. Acceleration is dv dt. And then you want to differentiate what the velocity is. Because it's pretty obvious, isn't it, that when you differentiate that you get -2, which is a constant. So putting in those other lines just shows to the marker that you know what you're doing, which is a constant. So that's 1 mark there for part A, part 1. Part 2, find the time when the particle is at rest. So the particle is going to be at rest when velocity equals 0. So here's our expression for the velocity. We're going to make that equal to 0. Oh, sorry, it's not B, it's part 2. And solve for t, because the question is asking for when. When means find t. So 2t equals 10, so t equals 5. And t is in seconds, so it's 5 seconds, the particle is at rest. Part 3, show that the position of the particle after 7 seconds is 26 meters to the right. Okay, so we're given our expression for our velocity. We need to show that the position of the particle, which means its displacement, is 26, positive 26 when t equals 7. So how do we get displacement from velocity? Well, we need to integrate, because displacement is the integral of velocity with respect to time. So it means we need to integrate 10 minus 2t. And integrating that, you get 10t minus t squared plus c. What information do we have to find the constant? There we have it. When t equals 0, displacement equals 5. So you can see that equals 0, that equals 0, so c equals x. So the constant equals 5. So our displacement equation is 10t minus t squared plus 5. And then how can we use this to answer the question? Show that the position of the particle when t equals 7 is 26. So let's substitute in t equals 7. Just show that the answer is 26. So you want to show all the working out you can. 7 squared plus 5 It's 70 minus 49 plus 5. Put in your calculator and double check that the answer is 26. And displacement is in meters, so meters. Part 4, find the distance travelled by the particle during the first 7 seconds. Okay, now we've already found up here that the particle was at rest when t equals 5. So that means our particle is, where was it initially? Initially the particle was 5 meters to the right of the origin. So it's initially at 5 meters to the right. It is moving along. When t equals 7, it's 26 meters to the right. So with our number line here, we will put 0 here, where we have 5, 10, 15, 20. 26 is just here. So initially it is at t equals 5. The particle is moving up to 26. And at t equals 7 it is at 26. And at t equals 5 it was at rest up here. So that means, where is the particle at 5 seconds? Because it's starting at t equals 5 and ending at 26. But what's happening in between when the particle is at rest? Where is the particle when the particle is at rest? Well, let's find where it is, what the displacement is when t equals 5. So we've got 10 times 5 minus 5 squared plus 5. 50 minus 25 plus 5 is 30. So that's when t equals 5. So that means our particle is starting at 5, it's moving all the way up to 30, and then it's turning around for the last 2 seconds and coming back to 26. So how far has that particle travelled? Well, it's from 5 up to 30. How far is that? We need another colour here. Distance travelled. Where can I put that? Maybe I'll squeeze it in here. From 5 up to 30. Well, 30 minus 5 is 25. So it's moved to 25. And then how far has it travelled going from 30 to 26? Well, that's going to be another 4 metres. So it's travelled 25 metres. And then it's travelled 4 metres, so it has travelled a total distance of 29 metres. If we were to work out this question using the integral, the distance travelled is the integral between, we can't just say in the first 7 seconds, we can't just say between 0 and 7, because we know the particle is at rest at t equals 5. But what you could do is work out the integral between 0 and 5. And you could also work out the integral between 5 and 7 and add those together. So both of those are dt. So adding those together, now your integral between 5 and 7 of the velocity is going to end up being a negative number. So you need to put absolute value signs there. So and you'll get the same answer. The answer is going to be 29 metres. And I just want you to double check that by completing this integration and this integration. Thanks.